All right, now we're going to go into different properties of the derivative of the vector valued functions. Numbers 1, 2, 3, and 6 all should work about how you would expect them to. First of all, number 1, if we have some sort of scalar multiplied, so in this case c is a scalar, we take the derivative of a scalar times a function or a vector valued function, we can pull the scalar out. It's the same as what we would have as a scalar multiplication in a regular derivative. Similarly, number 2, if we take the derivative of two different vector valued functions that we're either adding or subtracting, we can just take the sum or difference of that derivative, of those derivatives, and that would be fine. Again, the same thing that you would have done in Calculus 1. The scalar product works, this works like the product rule from Calculus 1. So if you notice here, we're taking the derivative of a product of two things. One is a regular function, and the other is a vector valued function. Well, in this, we have the derivative of the first, so derivative of our f of t, multiplied by the second, plus the first times the derivative of the second. That works the exact same way as the product rule does in regular calculus, as does the chain rule. Again, similar to Calc 1. These dot product and cross products are going to be new. You know how to take a dot product and a cross product now. On this video, I'm going to show you an example of how to do the dot product using Formula 4, and on the next one, I'll do one using a cross product example. All right, so here, in order to take the dot product, now it's going to be the derivative of the first dot the second, not multiplied. We've got the dot intersected there. Or inserted there. And we're going to add that to the first vector valued function dot the derivative of the second vector valued function. So for this problem number 61 that I have down here, this is the R and the S for each of these. So I'm going to need the derivatives of each. So let's do that first. So R prime of t. This is just I, the derivative of t is 1, and plus 2j minus 4t, this is cubed k, and this should be, instead of just 2j, it should be 2tj. All right, and then the derivative of s, derivative of sine is cosine. Derivative of e to the t is just e to the t. And then derivative of cosine is negative sine. So ultimately, this equals 1, 2t, and negative 4t cubed. And this one equals cosine t, e to the t, and negative sine t. So I'm going to scroll down a little bit. Still have that formula up there. All right, so now we're going to take the dot product. We're taking this dot product here. Okay, the derivative of the dot product. All right, and this equals, we have to take the derivative of the first one. So this is going to be 1, 2t, negative 4t cubed dot the second one, which in component form is going to be sine of t, then e to the t, and then cosine t. And this is going to be plus that second bits, which is the first, and then dot the derivative of the second, so what we have above there, and there should be a closure there. All right, remember that when we take the dot products, we simply multiply each component, the x's by the x's, the y's by the y's, and so forth, and then add up all of the values. So this is going to equal 1 times sine of t plus 2t e to the t minus 4t cubed cosine t. That's our first dot product, and then we add the second one, which is t cosine of t plus t squared e to the t. We've got a minus t to the fourth and a minus sine, so it's going to be plus t to the fourth sine of t. And we can probably clean this up a little bit. We want to keep like the sines and cosines together. We can certainly do that. So this is going to be 1 plus t to the fourth times sine of t. And then we can factor out a t, I guess. I don't know that matters. We can take out an e to the t and multiply it by 2t plus t squared. And finally, we can have a cosine out, which will give us t minus 4t cubed cosine t. It's sort of cleaned up, so I'm going to just leave it at that.